We come now to the very famous electrolyzer built by Bob Boyce of America. Most people wish to increase the number of miles per gallon travelled by their vehicle. Engine designs which give more than 240 miles per US gallon have been built by professional car manufacturers, but those designs will never be released to the public. However, other methods are available to us for getting really major improvements in vehicle performance. The most simple and cheapest of these engine upgrades are called boosters, and they usually work by adding a mixture of hydrogen and oxygen gases, called HHO, to the fuel inside each cylinder of your engine. The most advanced upgrade is caused by adding a fuel reformer to your engine, and that adds water and magnetic enhancement to the fuel fed to your engine. An intermediate step is to add an electrolyser to your vehicle. An electrolyser is a very advanced version of a booster. A booster adds a small amount of hydrogen-oxygen gas mix to the air entering your engine, typically between 0.5 to 1.2 litres of HHO gas per minute, and that enhances the burning of the normal fuel that the engine uses, raises the engine power, burns off old carbon deposits inside the engine, and makes a smoother running and much longer engine life. The Bob Boyce electrolyser described here produces 100 litres per minute, and at that major rate of flow the gas becomes a fuel in its own right. Actually, 100 litres per minute is such a high rate that it's quite difficult to get it out of the electrolyser, and so it is often turned down to 50 litres per minute. When using a booster of any design, you need to realize that HHO gas is highly energetic. If it wasn't, it would not be able to do its job of improving the explosions inside your engine. HHO gas needs to be treated with respect and caution. It is important to make sure that it goes into the engine and nowhere else. It is also important that it gets ignited inside the engine and nowhere else. To make these things happen, a number of common sense steps need to be taken. Firstly, the booster must not make HHO gas when the engine is not running. The best way to arrange this is to switch off the current going to the booster when the engine is not running. It is not sufficient to just have a manually operated on-off switch, as it is almost certain that switching off will be forgotten one day. Instead, the electrical supply to the booster is routed through the ignition switch of the vehicle. That way, when the engine is turned off and the ignition key removed, it is certain that the booster is turned off as well. So as not to put too much current load on the ignition switch, and to allow for the possibility of the ignition switch being on when the engine's not running, instead of wiring the booster directly to the switch, it is better to wire a standard automotive relay across the oil pressure unit and let the relay carry the booster current. The oil pressure drops when the engine stops running, and so this will also power down the booster. An extra safety feature is to allow for the very unlikely possibility of an electrical short circuit occurring in the booster or its wiring. This is done by putting a fuse or a contact breaker between the battery and the new circuitry, as shown in this diagram here. You have the oil pressure sending unit, which powers down when the engine isn't running, and that is connected across the relay, and the relay switches on and off with that, and it takes the battery current, which comes via the breaker, the circuit breaker that is, via the relay to power the electrolyser or booster. There is a one-way valve after the electrolyser to make sure that you get gas flow from the electrolyser onwards and not back into the electrolyser as it cools down. The onward path of the gas is passed through a very simple device which is a container with at least 5-inch depth of water inside it. That causes bubbles to flow upwards through the liquid and on into the area at the top of the container. That is then passed on to a second identical booster, which is close to the engine, and the output from that is fed directly to the air entering the engine as it normally would. If you choose to use a contact breaker, then a light emitting diode or LED with a current limiting resistor of say 680 ohms in series with it can be wired directly across the contacts of the circuit breaker. The LED can be mounted on the dashboard. As the contacts are normally closed, they short-circuit the LED and so no light shows. If the circuit breaker is tripped, then the LED will light up to show that the circuit breaker has operated. The current through the LED is so low that the electrolyzer is effectively switched off when the contact breaker opens. This is not a necessary feature, it's merely an optional extra. A good source for general components needed in building boosters and electrolyzers is the Hydrogen Garage in the USA. Its website is https://hydrogengarage.com. A very important safety item for any booster is the bubbler, which is just a simple container with some water in it. The bubbler has the gas coming in at the bottom and bubbling up through the water. The gas collects above the water surface and then is drawn into the engine. The onward feed from the bubbler to the engine is through a tube which starts above the water surface and so takes only the gas that's produced by the electrolyzer. To prevent water being drawn into the booster when the booster is off for any length of time and pressure inside it reduces, a one-way valve is placed in the pipe between the booster and the bubbler. If the engine happens to backfire, because of valve sticks or something like that, then the bubbler blocks the flame from passing back through the pipe and igniting the gas being produced in the booster. A bubbler is a very simple, very cheap and very sensible thing to install. It also removes any trace of electrolyte fumes from the gas before it's drawn into the engine. In practice, it's a very good idea to have two bubblers, one close to the booster and one close to the engine. The second bubbler makes sure that every last trace of electrolyte fumes are washed out of the HHO gas before it enters the engine. There are various ways to make a good bubbler. In general, you're aimed at having a 5-inch, that's 125 millimeter, depth of water inside the bubbler through which the HHO gas must pass before it leaves the bubbler. It's recommended that a bubbler is built inside a strong container, such as this one here, which is available in America. These strong containers are generally sold as water filters. They can be adapted to become bubblers without any major work being done on them. At this point, we need to consider the mechanism for moving the HHO gas out of the booster and into the engine. It's generally a good idea to position the gas takeoff pipe in the center of the lid of the bubbler, so that if the booster or bubbler get tilted due to the vehicle operating on a sloped surface, then the surface level of the liquid remains unchanged underneath the gas pipe. A common mistake is to use a gas pipe that has a small diameter. If you take a length of plastic pipe 1/4 inch in diameter, that's 6 millimeters, and try blowing through it, you'll be surprised at how difficult it is to blow through. There is no need to give your booster that problem, so I suggest that you select a gas pipe of 1/2 inch or 12 millimeters or so. If in doubt as to how suitable a pipe is, then try blowing through a sample length of it. If you blow through it without the slightest difficulty, then it's good enough for your booster. All of the practical construction details on electrical safety, gas safety, engine connections, type of water, safe mixing of electrolyte, etc. apply to all kinds of electrolyzers and boosters of every design. So please understand that these are universal features which need to be understood when using any design of booster. It's possible to produce large volumes of HHO gas from a DC booster, enough gas to run a small motor directly on it. For this we need to pay attention to the efficiency factors. The person who is outstanding in this field is Bob Boyce of the USA, who has kindly shared his experience and expertise freely with people who want to use serious electrolyzers. I have no hesitation in describing Bob Boyce as a genius. Bob's attention to detail when constructing high-performance electrolyzers has resulted in efficiencies which are more than double those of the very famous Michael Faraday, whom most scientists, or so-called scientists, consider to be the final word on electrolysis. Serious electrolyzers are not cheap, weigh a considerable amount, require considerable skill to make, and usually are quite large physically. Bob makes his solid stainless steel electrode plates act as cell partitions as well as being electrodes. This is a clever technique, but it takes a very high level of construction accuracy to make a box with slots in the side and base so that the stainless steel plates can be slid into the box and when there form a watertight seal between the cells, preventing electrical current bypassing plates by flowing around them. The number of cells in the electrolyzer depends on the electrical DC voltage supply which is produced from the electrics of the vehicle. This higher voltage is created by using a standard off-the-shelf American inverter which produces high voltage alternating or AC current, meant to be the equivalent of the local electricity main supply. In the USA, the voltage produced is in the 110 to 120 volt region. Elsewhere in the world, it is in the 220 to 230 volt region. If you're not familiar with electrical jargon, then check out the electronics tutorial which explains things step by step. The AC output from whatever inverter you buy is changed back into DC by using a component called a diode bridge and a reservoir device called a capacitor. When this is done, the resulting DC voltage is 41% greater than the quoted AC voltage. So a 110 volt inverter will produce about 155 volts and a 220 volt inverter will produce about 310 volts. As you are using a 110 volt inverter, as you want about 1.5 to 2 volts per cell, the number of cells in Bob's electrolyzer is 100, which requires 101 steel plates. This large number of stainless steel plates, each sized at 6 inches, that's 150 millimeters, by 6 inches, which is 150 millimeters, and are square. It creates a substantial weight which, when it's increased by the weight of the case and the electrolyte, it's substantial. So the device you're making is a heavy device. The overall arrangement without the capacitor is like this. You have 100 cells in a row of electrolyzer in using the 101 plates inside the electrolyzer to form 100 separately contained volumes of electrolyte. The electrolyte is a mixture of water and a chemical, either sodium hydroxide or potassium hydroxide. They are the most effective and well proven components which are not used up as part of the electrolysis process. The output from the electrolyzer is fed via a gas tube through a bubbler, through a one-way valve, through a second bubbler, and then Bob Boyce says you pass it through a particle filter before passing it on to the engine. The voltage that's used to drive the electrolyzer is produced from the 12-volt battery and electrical system of the vehicle. It's used to power a 110-volt AC inverter, which is rectified by 4 diodes before being passed to the electrolyzer itself. The battery system flows to the inverter through a contact breaker or fuse and a gas pressure cut-off switch to prevent the gas pressure inside the electrolyzer becoming too high, and then through a relay to pass the current to the inverter itself. And that, in general, broad outline principle is how the system operates. A very high precision box for this style of electrolyzer can be made using the design of the late Ed Holgate of Florida, if you, and only if you are, a skilled fabricator. This is Bob Boyce's design as built by Ed. It is a substantial box, in this case made of a transparent material, and the 2 side plates are slotted. They're slotted with such tiny indentations that they don't really show in this photograph, but there is one plate at the end installed so you can see how that they fit into the sides and base of the box. This is the gas output tube, and interestingly, because the gas rate is so high, the holes into the gas outlet tube are along the top of the actual pipe. That's to prevent splashes from the bubbling material inside the electrolyzer from getting into the output pipe. The gas production rate is so high that it has to have holes drilled along the top in order to try to exclude spray and moisture from the massive rate of bubbles bursting at the surface of the electrolyte. The high efficiency of Bob's electrolyzers is due to his meticulous preparation and construction methods. You will notice that Bob recommends the use of a particle filter with a 1 micron mesh between the engine and the HHO system. Apart from ensuring that everything entering the engine is very clean, the particle filter with the mesh of that small size also acts as a flashback preventer, as flame can't pass through it. Firstly, the stainless steel plates are cross-scored with sandpaper to create a specially shaped plate surface, which helps high-speed bubble release. Secondly, the plates are put through a rigorous cleansing process where they are subjected to repeated periods of electrolysis, followed by rinsing particles off the plates and filtering the electrolyte solution. When no further particles break free from the plates, they're then put through a conditioning process which develops a catalytic layer on the plate surfaces. Bob Boyce is a most experienced and knowledgeable series cell designer, and sincere thanks are due to him for sharing his design freely with everyone and for his continuous help, advice and support of the builders of electrolyzers. Bob achieves a massively increased gas production rate by using an electrolyzer with a large number of cells in it. Bob's electrolyzer is easily the most effective available at this time. It uses 100 cells, that needs 101 plates, and he applies a sophisticated pulsing waveform which raises the operational frequency far above that envisaged by the science textbook available today. Units with just 60 cells are inclined more to brute force DC electrolysis, tending to mask the gains produced by electrical pulsing. As there is a voltage drop across each stainless steel electrode plate, it is usual to allow about 2 volts across each cell for DC operation. However, Bob finds that for high efficiency pulsing, the optimum voltage for each cell with 316L grade stainless steel electrode plates is about 1.5 volts. This means that a voltage of about 1.5 times 100, which is 150 volts, is needed to power it to its maximum pulsed output. To get this higher voltage, Bob uses a 110 volt inverter. An inverter is a common commercially available electronic circuit which usually has a 12 volt DC input and generates in America a 110 volt AC output. These are readily available for purchase as they're used to run US mains equipment from car batteries. The output from these inverters is converted from alternating current to direct DC current is by passing the output through 4 diodes in what is called a diode bridge. These are readily available at very low cost from electronic component suppliers. Obviously, it would not be practical to use 100 self-contained cells daisy-chained together to act as the series-connected electrolyzer cell. There would not be enough physical space in the engine compartment for that, so a different style of cell construction is needed. The view looking down on several separate electrolyzer cells could be represented something like this. Here the positive electrical supply is shown in red, the negative electrical supply is shown in blue, and each electrolyzer has got 5 separate active cells formed by 6 metal plates. That would be an effective way, certainly, of producing HHO gas in each individual electrolyzer, provided, of course, you apply the correct voltage across it. Here, the plus side of each cell is connected to the minus side of the next cell through the electrolyte to provide a set of 6 interconnected cells acting in series. The current flowing through the electrolyzer goes through each cell in turn, and so each cell receives exactly the same current as the other cells. This is the same sort of arrangement as using 6 self-contained cells in a daisy chain. To reduce the physical side of the unit, it's possible to construct the electrolyzer as shown here. If you look down from the top on the electrolyzer, you have a number of separate self-contained cells. In this instance there are 6 of them inside the box. Now if you do that, you've got wasted space between each individual electrolyzer. Ideally you don't want wasted space in it. So as each cell has got just 1 negative plate and 1 positive plate, the plates slot into the sides and bottom of the housing so that the electrolyte is trapped between the plates, and an air gap is formed between the plus plate of one cell and the minus plate of the next cell. These air gaps are wasted space. They contribute nothing to the operation of the electrolyzer. Each consists of a metal plate, a gap, and a wire connection to the next metal plate. From an electrical point of view, the 2 metal plates at the opposite ends of these gaps, being connected by a wire link, are effectively the same plate. It's just one very thick hollow plate. These air gaps might as well be eliminated, which would save 1 metal plate and 1 wire link per cell, not to mention the gap that you got rid of. This can be difficult to visualize, but it produces an arrangement like this. Looking down on the top, you see each individual plate between the pieces of electrolyte, the contained separate cells of electrolyte, are divided by a plate, which you can think of as having a positive electrical connection on one side and a negative electrical connection on the other side, and the plate being embedded in the base of the case acts as a separator between separate individual sections of electrolyte. It's effectively the same arrangement as your original multi-celled container here, but it is much more compact, and though it looks odd if you're not familiar with what's happening, it is electrically exactly the same. The only gaps remaining then are at the end of the electrolyzer. The plates in the midden are notionally touching each other. The positive plates are marked in red, the negative plates are shown in blue. In reality, there's only one metal plate between each cell and the next cell. The red and blue markings is only a notional device to try to make it easier to see that the diagram actually shows 6 separate cells in a single housing. They are separate cells because the metal electrode plates extend into the base and sides of the housing, thus isolating the 6 bodies of electrolyte from each other. It is very important that the different bodies of electrolyte are fully isolated from each other. Otherwise, the electrolyzer will not act as a series connected unit, and most of the current would skip past the middle plates and just run from the first plate to the last plate around the sides of the other plates. So the plates need to be a fairly tight push fit in the grooves cut in the sides and base of the housing. The electrolyte level must always be below the top of the plates, as shown in this diagram here. You have the gas output near the center of the total unit. The side view is the same, except that you can now see the electrical connections running to the end plates, and the plates are embedded securely and tightly in both the base and sides of the actual physical housing of the unit. An electrolyzer with 100 cells built in this style will have 101 metal plates and 100 separate bodies of electrolyte. In spite of these large numbers, the size of the overall unit does not have to be excessive. The spacing between the plates is set to typically 3 millimeters, which is 1/8 of an inch, and the plate thickness might be 16 gauge, which is 1/16 of an inch. So the width of a 100 cell electrolyzer is about 20 inches. In actual practice, the gaps at the end of the electrolyzer may also contain electrolyte, although the electrolyte takes no part in the electrolysis process. The size of the plates may be determined by the space available in the engine department. If there's a large amount of spare space, then the plate size may be selected by allowing from 2 to 4 square inches of area on both sides of each plate per amp of current. Each side of every plate is in a different electrolysis cell, so a 6-inch by 6-inch cell will have 36 square inches on each face, and so in theory could carry between 36 divided by 4, which is 9 to 18 amps of current. The choice of current is made by the builder of the electrolyzer, and it will be influenced by the size and cost of the inverter chosen to drive the electrolyzer, and the allowable current draw from the battery. This is for straight DC electrolysis, where the battery is connected directly across the electrolyzer. Using Bob's triple oscillator electronics pulsar card, the electrolyte level has to be kept down to about 3 inches from the top of the 6-inch plate, because the gas production rate is so high that there has to be substantial freeboard to stop the electrolyte being splashed all over the place. Bob uses a 6-inch by 6-inch plate size. It is essential that every item which contains HHO gas is located outside the passenger compartment of any vehicle. Under no circumstances should the electrolyzer or bubbler be located in the passenger area of the vehicle. As should any HHO be ignited, then the sound created by that ignition will be so great that permanent hearing damage would be a serious possibility. For straight DC operation of an electrolyzer of this type, the circuitry is very straightforward. The inverter should be mounted securely, preferably in the stream of air drawn in to cool the radiator. Using a diode bridge of 4 diodes converts the stepped-up AC output of the inverter back into pulsing DC and produces the electrical arrangement shown in this diagram. As mains voltage is quoted as an average figure, that is root mean square, it has a peak voltage of 41% more than that level that's quoted for the inverter. This means that the pulsing DC has a voltage peak of just over 150 volts for the nominal 110 volt AC output from the inverter. The bubblers and the particle filter remove all traces of electrolyte fumes from the gas, as well as protecting against any accidental lighting of the gas caused by engine misfiring. The very famous Michael Faraday, who was an exceptionally gifted experimenter, placed 2 electrodes in water and determined how much gas was produced per amp of current. Using an electrolyte and recent technology when running on DC, Bob Boyce would not consider an electrolyzer properly constructed, cleansed and conditioned until it was producing more than double Faraday's gas production rate. A typical working electrolyzer made by Bob would have about 216% of Faraday's result. People taught in universities and unaware of current technology use Faraday's results in calculations, and those calculations indicate that it would take more energy to produce HHO gas than could be produced by then burning the hydrogen generated. Their calculations are wrong. The energy in freshly made HHO gas is typically 4 times more energetic than hydrogen is. In fact, it can sometimes be 8 times as much. And so those calculations are too low by a factor of more than 8 times. Also, the majority of energy from burning HHO comes from charged water clusters and not from the hydrogen. And most of these good people doing the calculations have never even heard of charged water clusters. And so they accept the can't be done verdict without thinking about it. The next step forward in raising HHO production is to apply a suitable pulsed waveform to the electrolyzer terminals rather than just a straight DC voltage. Doing this with the design of Bob Boyce raises the cell efficiency to around 10 times the result produced by Michael Faraday. Bob Boyce's highly efficient pulse electrolysis system has been very generously shared freely by Bob, so that anyone who wishes may construct one for their own use without the payment of a license fee or royalties. Just before presenting the details, it should be stressed that in order to get Bob's performance of up to 1,000% of the Faraday's supposed maximum gas output, each step needs to be carried out carefully, exactly as described. Much of the following text is quoted from Bob's forum posts, and so should be considered as his copyright, not to be reproduced without his permission. We come now to your responsibility. If you decide to construct an electrolyzer of this or any other design, you do so wholly on your own responsibility, and nobody is in any way liable for any loss or damage, whether direct or indirect, resulting from your actions. In other words, you are wholly responsible for what you choose to do. I say again, This document must not be construed as an encouragement for you to construct this or any other electrolyzer. Bob's electrolyzer splits water into a mixture of gases which are mainly hydrogen and oxygen, though not exclusively so. That gas mixture, which will be referred to as HHO, is highly reactive and must be treated with respect and caution. A fairly small volume of HHO gas ignited in air is quite liable to cause permanent hearing loss or impairment due to the shock waves caused by the ignition. If HHO gas is ignited inside a sealed container, then the resulting implosion is liable to shatter the container. Bob uses two bubblers and a one-way valve to protect against this occurrence, and details of these are given in this document. To make the water inside the electrolyzer carry the necessary current, potassium hydroxide, that's KOH, is added to distilled water. This is the best electrolyzer for an electrolyzer of this type. Potassium hydroxide is also known as caustic potash and is highly caustic. Consequently, it needs to be handled carefully and kept away from contact with skin and, even more importantly, eyes. If any splashes come in contact with you, it's very important indeed that the affected area be immediately rinsed off with large amounts of running water and, if necessary, the use of vinegar, which is acidic. This electrolyzer design uses a toroidal transformer to interface the electronics to the electrolyzer cells. It is vital that this transformer be used very carefully. Under no circumstances may this transformer be powered up by the electronics when connected to anything other than the filled electrolyzer cells, as they act as a safety buffer. When driven by Bob's electronics, this transformer draws additional energy from the environment. While this is very useful for electrolysis, there are sometimes unpredictable energy surges which can generate as much as 10,000 amps of current. If one of these should occur when the transformer is not connected to the electrolyzer, which is able to soak up this excess, the resulting electrical conditions can be very serious. If you are lucky, it will just burn out the expensive components of your unit. If you're not lucky, it can cause a lightning strike which is able to hit you. For that reason, it is absolutely essential that the toroid transformer is never powered up with the secondary winding connected to anything other than the filled electrolyzer. We come now to the subject of patenting, and it should be clearly understood that Bob Boyce has released this information into the public domain, and it has been displayed publicly since early in 2006. It is not possible for any part of this information to be made part of any patent application anywhere in the world. This prior public disclosure of the information prevents it being patented. It is Bob's intention that this information be freely available to people worldwide. It should also be emphasized that all of the quotations of Bob's words, which is a very extensive part of this document, remain the copyright of Bob and may not be reproduced for display or sale without his prior written permission. We come now to the objective. This is an HHO on demand, that is HOD, system. It is very difficult indeed to generate the HHO gas fast enough to power an internal combustion engine vehicle under all road conditions. Moving from standstill to rapid acceleration causes such a massive sudden requirement of additional volumes of HHO gas that it is difficult to provide that volume instantly. A better solution is to use an electric engine for the vehicle. This can be an electrical vehicle which was designed from scratch, or it can be a standard vehicle which has been adapted for electrical engine use. These electric vehicles are usually limited in how far they can travel, but a good solution to this is to use an electrical generator to charge the batteries, both when the vehicle is in use and when it is parked. This electrolyzer can be environmentally friendly, and it can be used to run a generator of that particular type on water. With this arrangement there are no carbon dioxide emissions, and the vehicle is very environmentally friendly. The batteries provide the necessary sudden acceleration demands, and the generator recharges the batteries during normal driving. Bob's pulse system has the following components. One is an electrical connection to the vehicle's electrical system, with safety features built in. Two, an inverter which raises the electrolyzer voltage to about 155 volts. 3. Bob's specially designed circuit board which generates a complicated water splitting waveform. 4. Bob's specially designed toroidal transformer which links Bob's circuit board to the electrolyzer. 5. Bob's specially prepared 101 plate series connected electrolyzer. 6. A dual protection system for linking the electrolyzer safely to the internal combustion engine. None of these items is difficult to achieve, but each needs to be done carefully and exactly as described, paying particular attention to the detailed instructions. Building the case. The case needs to have very accurate slots cut in it. If you do not have a milling machine, then you might consider getting a fabrication shop to mill the slots for you. The case has two ends, two sides, one base and one lid. Of these, the two sides and the base need 101 accurate grooves cut in them. The grooves are there to hold the electrode plates securely in position and have to be cut extremely accurately. The groove width is set at 0.0003 inches, less than the actual measured plate thickness. This prevents any electrical flow around the plates. Many people ask about molding the slotted sides, but this is physically impossible due to the accuracy needed, and the cell performance depends on spacing to a very high accuracy and slot width to be even higher accuracy. This is not a backyard construction quality job, and there are very, very few people with both the equipment and the skill to complete the construction of the case to this high degree of accuracy. The case itself is shown in this diagram here. You have a 1/8 inch or 3 millimeter gap between the faces of the plates. You have the plates inserted very tightly into extremely accurately cut slots in the base, and the same applies to the sidewalls. Now, as that's not easy to do by any means, it's easier to arrange it so that the base and the two sides of the cell are fashioned out of a different material. The steel plates expand when they warm up, and they're liable to crack the case, which is made out of acrylic plastic, unless the slots are cut deeper than normal. Also, it's difficult to cut very accurate slots in acrylic due to the heat of the cutting blade. That causes the acrylic to deform in the immediate area. Grooved acrylic is very much weaker and breaks easily due to the planes of weakness introduced by the slotting in the material. Using ultra-high molecular weight polyethylene or high-density polyethylene, which is food chopping board material, strips, is a much better technique, as that material does not have the same cutting heat problem, and it can also take the plate expansion much better. So it is the construction method of choice. It's also a cheaper material. The grooves are cut for the plates should be 3/1000 of an inch wider than the thickness of the plates. A good plate thickness is 16 gauge sheet, which is 1/16 of an inch thick, or 0.0625 inch, or 1.15875 millimeters in the gap width. So the recommended groove width for that is 0.0655 inches, which is not a convenient fraction, being about 4 1/5 64ths of an inch. The grooves are 1/8 of an inch, which is 3 millimeters deep. The supplier of the acrylic sheet needed for making the case will also be able to supply what you might call glue, specifically designed for joining acrylic sheets together. This glue actually welds the plates together so that the sheets become one continuous piece of acrylic along the joint. Start by mating the sides and the base. Insert 2 or 3 plates into the side slots to be quite sure that the alignment is spot on during this joining process. Line the ends up during jointing to be sure that the sides are completely square when being joined to the base. Concerns have been expressed about the strength of the acrylic casing under severe road conditions, so it has been suggested that the acrylic components be constructed from sheet acrylic, which is 3/4 inch to 1 inch thick, that's 18 to 25 millimeters thick, and the corners reinforced with angle iron secured with bolts tapped into the acrylic, as shown in this diagram here. This is the UHMW PE strip attached to the side of the acrylic. This is the same sort of strip attached to the base, and that is done before the box is actually physically constructed. The steel angle strip is then used to make a reinforcement along the corner of the case itself to reinforce the case. This is the photograph below here is the 101 plate housing built by the late head Holgate, who worked to a very high standard of accuracy. These are the side sheets which you can see through the acrylic. The acrylic is transparent. These are the plastic facer sheets with the slots cut in them. And as I said before, the slots are so tiny that it's extremely difficult to see them. You can just about see them in this corner of the photograph here. The extraction of gas is through the pipe with the holes drilled on the top. The supply of additional water is through this water supply pipe, which has holes drilled over the individual cells on the underneath side of the pipe, so that the water is dripped accurately into the actual cells. The housing looks very simple and straightforward, but that's highly misleading, and the materials are very expensive, so any error is costly. The construction accuracy needed is very high indeed, with many opportunities for a total and expensive disaster. Ed Holgate has built several custom fixtures to ease the construction, but construction is still very difficult even with these specialist fittings and his years of experience. Sikaflex 291, or marine goop, marine bedding component, can be used to seal between the 2 slotted sides and the slotted base, and between the slotted sides and the 2 end inserts, in order to prevent any leakage between the acrylic and any of these inserts. The accuracy required for the slots to hold the stainless steel plates is 0.0003 inches, and the plates are tapered with a belt sander on both sides along all 4 edges, so that when they are forced into the slots they will not cut cut into the sides of the slots. This produces excellent leakage characteristics, but don't lose sight of the very high accuracy of the slot cutting needed for this. The edges of the slotted inserts receive a bead of Sikaflex marine bedding compound attaching them to the acrylic box, and the compound is allowed to cure before the construction is continued. The end plates with the stainless steel straps welded to them are used to connect the electrical supply to the plates, keeping any connection which could possibly work loose and cause a spark completely outside the housing. Even though the straps are welded and there's no likelihood of them coming loose, the welds are still kept below the surface of the electrolyte. We come now to getting and preparing the plates. A set of 101 plates is needed for the electrolyzer. The material used when making the plates is very important. It should be 16 gauge 316L grade stainless steel, as that contains a blend of nickel and molybdenum in the correct proportions to make it a very good catalyst for the pulsing technique. You can try your local steel stockist to see if they can supply it and what their charges would be. One satisfactory stainless steel supplier which Bob has used is Intertrade Steel Corp, 515 Mount Vernon Road, SE, Cedar Rapids, 1A52406. Do not buy from eBay, as you've no real comeback if the plates supplied are dished due to having been flame cut. It is very important indeed that when asking for a quote you make sure that the supplier is aware of the accuracy that you require. The plates need to be flat to a tolerance of plus or minus 0.001 inch after cutting, and this is the most important factor. That level of accuracy excludes any kind of flame cutting, as that produces inevitable heat distortion. With shearing, expect plus or minus 0.015 inch on the cuts and plus or minus 0.001 inch on flatness. Laser cutting produces much higher accuracy, and you can expect as good as plus or minus 0.005 inch on cuts, and there is no spec needed for flatness, since laser cutting does not distort the edges like shearing does. The plates are square, 6 inches by 6 inches, but that does not represent 36 square inches of active surface area, as some plate area is inside the grooves and some of each plate is above the surface of the electrolyte. Another point to remember is that 101 steel plates of this size weigh a considerable amount, and the completed electrolyzer with electrolyte in it will weigh even more. It's essential therefore to have a case which is strongly built from strong materials, and if a mounting bracket is to be used, then that bracket needs to be very robust and well secured in place. The preparation of the plates is the most important step in producing an electrolyzer which works well. This is a long task, but it is vital that it is not skimped or hurried in any way. Surprisingly, brand new shiny stainless steel is not particularly suitable for use in an electrolyzer, and it needs to receive careful treatment and preparation before it will produce the expected level of gas output. The first step is to treat both surfaces of every plate to encourage gas bubbles to break away from the surface of the plate. This could be done by grit blasting, but if that method is chosen, great care must be taken that the grit used does not contaminate the plates. Stainless steel plates are not cheap, and if you get grit blasting wrong, then the plates will be useless as far as electrolysis is concerned. A safe method which Bob much prefers is to score the plates to score the surface of the plates. This is done in an unusual manner. Bob does sometimes use a sanding belt, but he says the safe method, which he easily prefers over all others, is to score the plates with coarse sandpaper. This is done in two different directions to produce a crosshatch pattern on the surface of the shiny stainless steel plate. The scoring is done in two different directions to produce a crosshatch pattern. This produces microscopic sharp peaks and valleys on the surface of the plates, and those sharp points and ridges are ideal for helping bubbles to form and break free of the plates. Bob Boyce uses a specially widened 48-inch belt sander, which is good for preparing the plates using 60 or 80 grit belt. However, most people don't have this equipment and do the sanding by hand. Bob stresses that when doing hand sanding, the sandpaper is drawn across the plates in one direction only, and not backwards and forwards, as the backward stroke always destroys the perfectly good ridges created on the forward stroke. Also, you only need 2 strokes in one direction before turning the plate through 90 degrees and completing the sanding of that face of the plate with just 2 more strokes, again with no backstroke. Most people want to sand the plates far too much, and if overdone to a major degree, that can reduce the plate thickness and cause electrolyte leakage through the slots around the plates. So, to say it again, to sand one face of a plate, use just 2 strokes in one direction, turn the plate through 90 degrees, and finish that face with just 2 more strokes, both in the same direction. Always wear rubber gloves when handling the plates to avoid getting finger marks on the plates. Wearing these gloves is very important, as the plates must be kept as clean and grease-free as possible, ready for the next stages of their preparation. Any particles creating by the sanding process should now be washed off the plates. This can be done with clean tap water, but not city water though, due to the chlorine and other chemicals added, but only use distilled water for the final rinse. A point which is often missed by people containing electrolyzers is the fact that electrolysis is not just an electrical process, but it's also a magnetic process. It's important for the operating efficiency that the plates are aligned magnetically. Now this is something that I'm saying, not that Bob's saying. Bob was dismissive of this as a notion when he first saw it, but subsequent people, having built and tested it, find that in their case their quality of stainless steel is not as high as Bob's, and so it makes a considerable difference to them. In theory, stainless steel is not magnetic, but much stainless steel actually supplied to builders is slightly magnetic. When the plates arrive from the supplier, each plate may have a random magnetic characteristic. The easiest way to deal with this situation is to try to give the plates a mild magnetic orientation. This can be done quite simply by wrapping a few turns of wire around the stack of plates and passing some brief pulses of DC current through the wire. So you stack the plates up, wind a few turns of wire around them, and tap the wire to a battery a few times. That will align the magnetic characteristics of the plates all in the same direction and the same way. If your plates are perfect and are excellent stainless steel, they'll not be magnetic at all, so you can't harm anything by doing this. If your plates are perfect, it won't give any advantage, so there's no harm in doing it, and there's no disadvantage in not doing it. Let me rephrase that. Do it. is the simple answer. Obviously, the plates need to be kept in the same direction when being slotted into the case. The next step in the preparation process is to make up a weak solution of potassium hydroxide. This is done by adding small amounts of the potassium hydroxide to the water in a container. The container must not be glass, as that's not a suitable material in which to mix the electrolyte. Potassium hydroxide, also called KOH or caustic potash, which can be bought from suppliers. It can be bought from various suppliers such as the essentialsdepot.com, the organiccreations.com, or the newsensecandle.com suppliers, while potassium hydroxide KOH and sodium hydroxide NaOH are the very best electrolytes. They need to be treated with care. The handling for each is the same, always stored in a sturdy, airtight container which is clearly labelled Danger Potassium Hydroxide. Keep the container in a safe place where it can't be reached by children, pets, or people who won't take any notice of the label. If your supply of KOH is delivered in a strong plastic bag, then once you open the bag you should transfer all of its contents to sturdy, airtight plastic storage containers, which you can open and close without risking spilling the contents. Hardware stores sell large plastic buckets with airtight lids that can be used for this purpose. When working with dry KOH flakes or granules, wear safety goggles, rubber gloves, a long sleeve shirt, socks and long trousers. Also, don't wear your favourite clothes when handling KOH solution, as it's not the best thing to get on clothes. It's also no harm to wear a face mask which covers your mouth and nose. If you're mixing solid KOH with water, always add the KOH to the water and not the other way round. And use a plastic container for the mixing, preferably one which is double the capacity of the finished mixture. The mixing should be done in a well ventilated area which is not drafty, as air currents can blow the dry KOH around. When mixing the electrolyte, never use warm water. I'll say that again. Never use warm water. The water should be cool, because the chemical reaction between the water and the KOH generates a good deal of heat. If possible, place the mixing container in a larger container filled with cold water, as that will help to keep the temperature down, and if your mixture should boil over, it will contain the spillage. Add only a small amount of KOH at a time, stirring continuously, and if you stop stirring for any reason, put the lids back on all containers. If in spite of all precautions you get some KOH solution on your skin, wash it off with plenty of running cold water and apply some vinegar to the skin. Vinegar is acidic and will help balance out the alkalinity of the KOH. You can use lemon juice if you don't have vinegar to hand, but it's always recommended to keep a bottle of vinegar handy. We now come to plate cleansing. Plate cleansing is always done with sodium hydroxide, NaOH. Prepare a 5% to 10% by weight sodium hydroxide solution and let it cool down. A 5% solution by weight is 50 grams of sodium hydroxide in 950 cc's of water, because 1 cc of water weighs exactly 1 gram. A 10% solution by weight is 100 grams of NaOH in 900 cc's of water. As mentioned before, never handle the plates with your bare hands, but always use clean rubber gloves. Put the sanded and rinsed plates into the slots in the electrolyzer case, keeping them all the same way around so that they remain magnetically matched. Fill the electrolyzer with the NaOH solution until the plates are just covered. A voltage is now applied across the whole set of plates by attaching the leads to the outmost two plates. This voltage should be at least 2 volts per cell, but it should not exceed 2.5 volts per cell. Maintain this voltage across the set of plates for several hours at a time. The current is likely to be 4 amps or more. As this process continues, the boiling action will loosen particles from the pores and surfaces of the metal. This process produces HHO gas, so it's very important that the gas is not allowed to collect anywhere indoors, such as on ceilings. After several hours, disconnect the electrical supply and pour the electrolyte solution into a container. Rinse out the cells thoroughly with distilled water and filter the dilute sodium hydroxide solution through paper towels or coffee filters to remove the particles. Pour the dilute solution back into the electrolyzer and repeat the cleaning process. You may have to repeat the electrolysis and rinsing process many times before the plates stop putting out particles into the solution. If you wish, you can use new NaOH solution each time you cleanse, but please realize that you can go through a lot of solution in just this cleansing stage if you choose to do it that way. When cleansing is finished, typically it takes 3 days of cleansing, do a final rinse with clean distilled water. It's very important that during cleansing, during conditioning, and during use that the polarity of the electrical power supply is always the same. In other words, don't swap the battery connections over, as that destroys all the preparation work and requires the cleansing and conditioning process to be carried out all over again. Plate conditioning then occurs. Using the same conditioning and concentration of solution as in cleansing, fill the electrolyzer with dilute solution up to 1/2 inch below the tops of the plates. Do not overfill the cells. Apply about 2 volts per cell and allow the unit to run. Remember that very good ventilation is essential during this process. The cells may overflow, but that's okay for now. As water is consumed, the levels will drop. Once the cells stabilize with the liquid level at the plate tops or just below, monitor the current draw. If the current draw is fairly stable, continue with this current conditioning phase continuously for 2 or 3 days, adding just enough distilled water to replace what is consumed in the process. If the solution changes color or develops a layer of crud on the surface of the electrolyte, then the cell stack needs more cleansing. Do not allow the cells to overfill and overflow at this point. After 2 to 3 days of runtime, pour out the dilute KOH solution and rinse out the electrolyzer thoroughly with distilled water. Now we come to cell operation. We mix up a full strength solution of potassium hydroxide, that is 280 grams of KOH added to 720 cc's of water. As it is 20% more effective in use than is sodium hydroxide, we always use potassium hydroxide rather than sodium hydroxide for the actual use of the cell. The filling of the electrolyzer depends on whether straight DC electrolysis is to be used or resonant electrolysis is to be used. For straight DC electrolysis, fill the electrolyzer to about 1 inch below the tops of the plates. The DC voltage applied to the electrolyzer will be about 2 volts per cell or a little less. So this 100 cell electrolyzer will have 180 to 200 volts applied to it. This voltage will be generated with an inverter. For resonant operation, fill the electrolyzer to only half the plate height, because the HHO gas production is so rapid that room has to be left for the gas leaving the plates. With resonant operation, about 1.5 volts per cell is used. Troubleshooting. Abnormally low current draw is caused by improper plate preparation or severe contamination. Take the plates out of the electrolyzer and start over again from plate preparation. Abnormally high current is caused by high leakage between the cells. This will require rebuilding or resealing of the electrolyzer case. 3. If current starts higher, then drops off, this means that the plates are contaminated. Take the plates out of the electrolyzer and start over again from plate preparation. We now come to building the electronics. Resonant operation of the electrolyzer requires the use of a DC pulsing system. Bob has designed an advanced system for this, consisting of a sophisticated electronics board and a finely tuned toroidal transformer which interfaces and matches the electronics to the electrolyzer. These are available in kit form from the Hydrogen Garage in America, that is hydrogengarage.com, and these electronics boards produce 3 separate frequencies which are combined together to give a rich and complex output waveform, further modified by the toroidal transformer. This diagram shows the arrangement. You have a simple oscillator made from a 555 chip running at 42.8 kilohertz. That requires a 100k resistor and a 10 nanofarad capacitor. You also have a second 555 chip oscillator which operates with a 100k resistor and a 22 nanofarad capacitor. You have a third one which is also a 555 chip which uses a 100k resistor and a 47 nanofarad capacitor. Then, following those 3 waveforms which are generated by these 3 oscillators, you have variable frequency gate circuits which change the amount of signal which is allowed to pass through them. That breaks up the regular signal frequency into separate groups of pulses. Those are then fed to a driver circuit which feeds them on to a toroidal transformer which combines the 3 signals. In Bob Boyce's electrolyzer build, those frequencies were about 42.8 kilohertz, 21.4 kilohertz and 10.7 kilohertz. But please don't get the wrong impression here. There is no single exact frequencies or set of frequencies which should be used. The size and shape of your cell, the electrode spacings, the electrolyte density, the electrolyte temperature, and the operational pressure are all factors which affect the tuning of the electronics. With Bob's large marine duty cells with square 12-inch plates, which he used when racing his boat, he found that the base resonance point using this original modified inverter to be at least 100 cycles per second lower than the prototypes with smaller plate sizes. The triple oscillator board can be tuned with an oscilloscope, but if one is not available, then the preset resistors are set to their midpoint, and then the 42,800 cycles per second frequency is adjusted very slowly to find the point of maximum gas output. This is a very precise point, and it's essential to use high quality preset resistors which vary their resistance very accurately. The aim is to adjust the frequency by as little as 1 cycle per second at a time. When the optimum point is found, then the process is repeated with the 21,400 cycles per second frequency generator, and finally with the 10,700 cycles per second frequency. Last of all, the mark space ratio presets are adjusted to give the lowest pulse width, which does not reduce the rate of gas generation. When he tried separate flooded cell connections in series, Bob was not able to get anything more than a marginal rise in performance over a broader range. He felt that this was due to each cell in the setting having a slightly different resonant point which did not match very well with the other cells. Bob had to go to the series plate design with accurate spacing and high tolerance on slots and plates in order to get the resonant response to line up on all cells. Also, he found that some choices of electrolyte would not produce resonance at any frequency, although he's not sure why. Some worked well, while others worked marginally. So Bob stuck with what worked the best for him: sodium hydroxide, NaOH, and potassium hydroxide, KOH. It needs to be stressed here that every electrolyzer build is slightly different from all others, even though they may have been meant to be exactly the same. There will be small differences between plates in one electrolyzer and the plates in other electrolyzers. The electrolyte concentration will be slightly different. The plate preparation will be slightly different. The overall magnetic characteristics will be unique to each actual build. For that reason, the tuning of the completed electronics board and the construction of the best possible transformer to match the electronics to the electrolyzer is always different for each electrolyzer build. The completed third generation Bob Boyce electrolyzer board looks like this. You have the various chips. These ones here are 556, which are chips which contain two 555 circuits in each. The arrangement of the drive circuit for the field effect transistors which power the output is organized on this printed circuit board. That sort of circuit board is available from the Hydrogen Garage. It's not too difficult to assemble the board, as the printed circuit board can be purchased ready-made, and completed sets of components can be ordered from the Hydrogen Garage. The arrangement of the board seen at an angle is like this. You can see the screw heads here for the adjustments of the high precision preset resistors. It's a very neat board construction. The board is lifted off the metal cell, or the metal container box I should say. The container box is acting both as a protective container for the board and as one continuous heatsink plate for the field effect transistors, which are actually physically bolted to the board. The transistors are all bolted to the case, but each has its own rectangle of mica washer between the transistor and the case. These pieces of mica pass heat very readily to the case, while at the same time isolating the transistors electrically so that they will not interfere with each other. Notice too the plastic support columns on each corner of the printed circuit board. These are used to mount the printed circuit board securely while holding it away from the metal case, and so preventing any possibility of the connections on the underside of the board being short-circuited by the case itself. In some of the builds of the electronics board, it has been found that sometimes it's difficult to get the highest frequency oscillator operating correctly at 42.8 kHz due to some NE5556 chips being out of specification, even though they should be the same chips from different manufacturers. And even the same branded chips from different suppliers can have slightly different actual specifications. On both the PWM3E and PWM3F boards, C4 has now been changed from 0.1 microfarad back to 0.047 microfarad to accommodate the corrected specifications of the newer Texas Instruments NE556N chip, the one marked with Malaysia on top. The earlier versions of the NE556 chip required a change to 0.1 microfarad to correct for specifications that were substandard. Depending on which chip you actually use in the U1 to U3 board positions, you may have to adjust the value of C1, C3 and C4 to compensate for variations of the original 556 chip specifications, or adjust some of the other timing component tolerances. The Taiwan marked and other Texas Instruments chip will still work okay in the U2 and U3 locations, but there has been a big issue sourcing chips that will reach 43 kHz in the U1 location. The Malaysia chips tested so far have been satisfactory. It should be noted that it has been suggested that dividing the highest frequency signal by a factor of 2 to give the second highest frequency, and dividing it by 2 give the third highest frequency, is an accurate way of producing the three frequencies. That is in theory correct, and it will work to some degree, but it has been found that you get much better physical operation of the device if you use free running oscillators. So in actual fact, you get a better output from the overall system if you use the three oscillators as described in this document. Using the divided ones gives an output all right, but you don't get as big an output as with the free running ones. So it's definitely recommended that you build it as shown in this document. Setting up the completed board involves using jumpers, and the operation and position of the jumpers is shown here in this effective table. This is the underside of the printed circuit board, which has now been superseded by a more advanced board. The components on the board are shown here, and the way that you operate the board is shown with the various jumper positions here. The testing and operation and tuning of the board are all described here in detail, and if you have a board like this, you should deal with the components this way. If you have any heating issues with the metal oxide resistors, they may be removed and replaced with higher voltage metal oxide devices. Bob also says the most common mistake that I see made is that when tuning for the common narrow 2 microsecond pulse width on all channels, most people tend to tune for narrow positive going pulses at the FET outputs. That is totally inverse to proper pulse polarity for the PMW3 series boards. These boards use N-channel FETs, so the proper pulses are narrow negative going pulses. FET off condition results in a positive state on each of the outputs, so proper FET switching pulls that proper state to ground as very narrow pulses. We come now to the transformer. The transformer is very, very important. It's an inductor, a transformer. That is a coil and a source of energy form conversion, all rolled into one. The transformer has been successfully duplicated and used by others. Driven with Bob's triple oscillator board to achieve a resonant drive to the cells, which results in a performance which is well beyond the maximum stated by Faraday. The reason there are no step-by-step instructions for constructing the transformer is because it must be wound to match the load and impedance of the cells it will be driving. There is no one transformer fits all style solution for this. Bob uses a powdered iron core of 6.5 inches in diameter for units up to 100 cells. The larger the diameter, the greater the power. Ferrite is fine for lower frequencies, but for this application a powdered iron toroid core is essential. The micrometals core, part number T650-52, is a suitable core and is available from micrometals.com and can be purchased in small quantities via their samples request division, which can be submitted at micrometals.com/samples_index.html. These are the dimensions here of the toroidal coil itself. The outer diameter is 6.5 inches or 165 millimeters. The depth of the core is 2 inches, which is 50 millimeters, and the inner opening diameter is 3.5 inches, which is 90 millimeters. The primary of the transformer is three phase, while the secondary is single phase. As most current flows along the outside of wires rather than through the middle of the wire, the choice and size of the wire for winding the transformer is most important. Bob uses solid, Teflon-covered, silver-plated copper wire. It's very important that this wire is solid core and not stranded. A stranded wire does not work here due to the generation of interstrand phase differential induced eddy currents. At this time, the supplier of this wire is apexjr.com. Before any winding is done, the toroid is given a layer of tape, and the materials to be used are collected together, namely the tape, the wire, the beeswax, and the heat gun. Of major importance with the toroid is that, unlike traditional transformers, the secondary is wound first, and the windings must be evenly spaced where they fan out from the center of the coil. This means even though they are tightly packed up against one another at the center hole, they must not be wound so that they bunch up and gap open around the periphery. Mistakes here will cause field errors that will lower the overall efficiency. This is a photograph of a completed transformer. You will see that the windings are supposedly spaced evenly. This one is not quite perfect, but it's pretty good as such. The arrangement is made easier if you use a length of strimmer material, that's thick plastic diameter material. Short lengths of plastic strimmer wire can be used as spacers for the outside of the toroid, though this picture has been taken to show what a partially prepared secondary winding looks like when its windings are being moved into very accurate positions. You will notice that Bob has wrapped the toroid in tape before starting the secondary winding. Bob also uses a jar to assist in applying beeswax to the accurately positioned turns of the toroidal transformer. When the windings are completed, correctly spaced and encased in beeswax, each layer is finished off with a layer of tape. Bob says, I use a single wrap of PVC electrical tape stretched very tightly over the secondary winding, but be aware that the tension in the tape has a tendency to make it unwrap. A layer of the yellow 1P802 winding tape secures the electrical tape and holds it firmly in place, bridging triangular gaps between adjacent turns. Big warning here, do not use fiberglass winding tape. Let me say that again. Do not use fiberglass winding tape. A big box of 3M winding tape was ordered by accident, so I tried it, says Bob, to see if it would work. It not only suppressed the acousto-resonance response of the entire wound toroidal coil, but for some strange reason it also caused electrostatic pulse response of the secondary to reverse polarity and reducing the signal amplitude to a mere 10% of what it was. It totally negated the benefit of the Teflon insulation. I had to unwrap it and rewrap it with the yellow 1P802 winding tape. We had to return a whole box of this 3M winding tape and order more of the right stuff in bulk from Lodestone Pacific. So be warned, 3M fiberglass winding tape will totally ruin the behavior of the toroidal windings. So to recap, the toroid is wrapped in tape, the secondary wound extending the entire way around the toroid, the windings carefully spaced out so that the gaps around the outer edges of the toroid are exactly equal. The winding is encased in beeswax, then the beeswax covered with a thick layer of tape. The great majority of systems, the secondary winding is a tightly wound single layer full filled wrap of 16 gauge single core silver plated Teflon insulated copper wire. There will be about 133 turns in this winding, though it can vary from 127 to 147 turns due to manufacturing tolerances in the insulation of the wire. This will need a wire length of about 100 feet, and the whole of the toroid is covered by this secondary winding. Count the exact number of turns in your actual winding and make a note of it. This secondary winding is held in place with melted beeswax, and when that is hardened, the winding is then wrapped tightly with a good quality tape. This makes a good brace for the primary windings, which will be wound on the top of the layer of tape. The primary windings are started and finished paying attention to the direction of the turns being wound. Every winding starts by passing over the toroid and proceeds down through the opening and up around the outside, and that style of winding is called counterclockwise, and it finishes by passing under the toroid. Every winding is created in this way, and the quality of workmanship is very important indeed when making these windings. Each winding needs to be tight and positioned with the turns touching each other in the center of the toroid and positioned around the outer edge with exactly equal spaces. That's exactly equal spaces between each turn. Your construction work has to be better than that of a commercial supplier, and it needs to reach the quality demanded by the military, which would cost thousands of dollars for each toroid if it was to be made for you by professionals. So you have three primary windings, each wound in sequence around parts of the toroid itself. There are gaps between the three windings, and that will become because of the turns that you apply. These three windings are spaced out equally around the toroid, that is at 120 degree centers for the three, and the leads of the secondary windings exit through the gap between two of the primary windings and not in the middle of a secondary winding. The primary windings are held in place with beeswax and then tightly taped as the same way as the secondary, and the same care for even winding and spacing as the secondary is definitely needed. Tape the entire core well with tightly stretched PVC electrical tape after winding to ensure that the primary windings do not move, and then add an outer layer of winding tape. Bob uses the 1P802YE type on 3-inch rolls. Both the 1-inch and 2-inch whips are available from Lodestone Pacific. This is where the generic information ends. The exact details of the primary windings must be determined from the operational characteristics of the cells. This means that you must build, cleanse, and condition your cells prior to making the operational measurements. This is done as followed. After a full plate cleanse, as described earlier, conditioning the plate stacks reaches at least 150%, but ideally 200% or more of Faraday's maximum power efficiencies, which is 1.34 watts per hour, 1.34 watt hours per litre per hour. Then allow the cell stack to cool to room temperature. The cell stack is then powered up with a variable voltage power supply, and the voltage adjusted until the cell current is exactly 2 amps. Write down the voltage needed to give this 2 amp current flow, and do it promptly before the cell starts to warm up again. The objective here is to have the complex waveform generated by the electronics produce voltages of about 25% of this measured voltage. So divide your measured voltage by 4. The output from the electronics board is about 12.5 volts. To divide again by 12.5 to get the turns ratio for the toroidal transformer. This is normally in the range of 3.0 to 3.5, and that means that the secondary winding needs to have that times as many turns in it as each primary winding does. For example, an example only, say your measured voltage happens to be 155 volts. Then the turns ratio would be 155 divided by 4, which is 38.75. And then divide that by 12.5, which gives 3.1, which is the turns ratio. If your secondary winding has, say, 134 turns in it, then the number of turns in each of the 3 primary windings would be 134 divided by 3.1, which is 43.23 turns. Round this upwards to give 44 turns. If the number of turns which you use is off by 1 turn, then the tuning of the electronics board can compensate for it. If the number of primary turns is off by 2 turns, then it is possible that you might just be able to compensate for that error by tuning the board, but it's unlikely that you will. If the number of turns is 3 or more times away from the optimum number calculated by the impedance of the primary winding, then the optimum number calculated, the number of primary winding turns will definitely be too far out from the board to be able to use it. Normally the diameter of the wire used in the primaries will be greater than the secondary because it will be driven by a much lower voltage, and so you need a much higher current. But that is not the case here. Now that you've cleansed and conditioned the plates in your electrolyzer, power up your inverter with your vehicle engine running at 2000 RPM or so, and measure the DC current taken by the inverter. This is the level of current which the primary windings have to carry, so the wire size can be selected from this measurement. Each primary winding is pulsed and is not carrying continuous current all the time. Also, the final primary current is the sum of the three pulsing signals, so a reduction can be allowed for that. While the wire diameter for the primary windings of each toroidal transformer needs to be calculated separately, a common diameter turns out to be American wire gauge number 20, which is standard wire gauge number 21. 48 turns of American wire gauge number 20 are likely to require at least 35 feet, and that is for each of the three windings. Assuming that all turns can be laid side by side, if it is necessary to make a two-layer winding, then the wire length will increase further. But overall you're looking at typically 35 feet of wire on an ordinary single layer primary set of windings. That's 35 feet on each of the three windings. We come then to power limits. At the present time, the largest available on-powder toroid commercially available is the Micrometal's 6.5 inch unit. This sets the upper power limit for a Bob Boyce design electrolyzer at 32 square inches of plate area. Bob's present design uses 6-inch square plates, but the electrolyte is maintained at just 3 inches, and some area is effectively lost where the plates enter the walls and base of the housing. This 101 unit plate design, then built with precision and conditioned and tuned correctly, can generate 50 litres continuously and short bursts of up to 100 litres per minute. That is about 1 litre per minute of HHO gas per cell. This should be sufficient to run an internal combustion engine with a 1 litre engine capacity. But engines vary so much that there can be no rule of thumb for the gas production rate needed for a given engine size. In passing, may I remark that adding water vapour to the incoming air makes the engine operate very much better with only HHO gas as the fuel. The optimum operating voltage for Bob's 101 plate electrolyzer has been established by Bob as being 1.5 volts per cell. However, the power limitation of the 6.5 inch toroid does not prevent the voltage being raised. So if we opt for a 212 20 volt inverter rather than the 110 volt one already described, then the number of cells can be doubled. This extends the case from about 20 inches in length to around 40 inches. This might be suitable for use with vehicles up to 2 litre engine capacity, and the unit can be located on the flatbed of a truck or the boot or trunk of a car, or besides a generator. If it is being used to power an electrical generator, electrical generators are usually incredibly inefficient, with an overall efficiency of as little as 10% when the generator is considered. Consequently, running a generator on HHO gas alone is by no means as easy as it looks on the surface. If an electrolyzer is installed in a vehicle, it is very important that no pipe carrying HHO gas is routed through any passenger area, and a bubbler is positioned close to the engine, the number one priority must always be safety. Increased gas output can be got by increasing the width of the cells, which while maintaining the plate area covered by the electrolyte. One possibility is to make the plates 9 inches wide and keeping the electrolyte at a 4-inch depth, leaving a 36-inch square of plate area. The plate size would then be 9 by 6 or any other height up to 9 by 9. The reason why a Boyce electrolyser can give 1200% of the maximum possible gas output determined by Michael Faraday is that this unit pulls in large amounts of additional power from the environment. So the vehicle electrics is used primarily to power the pulsed toroidal circuitry, which taps this energy, and the conversion of water to HHO gas is primarily performed by the energy drawn from the environment. Plate surface preparation is very important, and it's described in detail. However, the way that the plates operate when used for straight DC electrolysis is quite different from the way that they operate when being used in high efficiency pulse mode. With the straight DC electrolysis, the bubbles of HHO gas form on the face of the plates and break away, helped by the thousands of microscopic sharp-peaked mountains created on the face of every plate by the two-direction scoring with sandpaper. With the pulse electronics, the HHO bubbles form in the electrolyte itself between the plates and give the visual impression of the electrolyte boiling. It should be realized that with the large volumes created with 101 plate and 201 plate electrolysers, that a considerable pipe diameter is needed to carry the gas, and even more importantly, the two bubblers need to be a considerable size. It's important that the bubbles streaming up through the water in the bubbler do not form a continuous column of HHO gas, as that would carry a flame straight through the bubbler and defeat the whole purpose of the protection which it normally provides. A good technique to combat this and improve the scrubbing of the electrolyte fumes out of the gas is to put a large number of small holes in the sides of the pipe carrying the gas down into the water of the bubbler. This creates a large number of smaller bubbles and is much more effective. We come now to connecting the electrics. Bob has specified that the primary windings are connected between the board outputs and the positive supply of the board, like this. You have the electronics board powering the various sections of the primary windings of the toroid. The secondary windings, I should say, are passed to the electrolyzer via the diode bridge, which feeds through a heavy-duty choke through the secondary winding to the electrolyzer. This looks like a fairly complicated method, but it isn't really. The battery and vehicle electrics through the safety circuit breaker and relay circuit feed the electrolyzer itself via a gas pressure switch. The gas pressure switch is important because the quality of HHO gas produced by this system is so high that if the gas is compressed to more than 15 pounds a square inch, it will automatically explode due to the electrical charge which it carries. The gas pressure switch therefore is set at a 15 pounds per square inch pressure, and if the gas inside the electrolyzer reaches that pressure, the pressure switch will disconnect the supply to the inverter diode bridge, and so the electrolyzer through the toroidal supply. There are heavy-duty chokes involved in this circuitry. They are available from Micrometals if you want to buy them, though you can wind them with just a few turns of wire yourself. The Micrometals number is T157-45. You need 3 of those. This circuit also uses a couple of capacitors. They're 200 volt 450 microfarad capacitors, and they work very nicely in this circuit, smoothing the output from the diode bridge before it is passed on to the rest of the circuitry. It is a neat arrangement, and you need to pay attention to both the position and connections to the primary windings of the toroidal coil. The number 1 output from the electronics board goes to the finish of the first winding. The start is connected through the heavy duty choke to the supply that continues on. Pay attention to the way that the primary windings are connected and to the order in which they're connected to the board. It's important to include heavy duty chokes in both sides of the high voltage power supply and in the 13.8 volt positive lead coming from the vehicle electrics. The recommended choke cores are the Micrometals T157-45. These are wound with 15 turns of American wire gauge number 16, which is standard wire gauge number 18, enameled copper wire. So it's perfectly okay to wind these chokes on laminated iron pieces taken from an old mains power transformer frame. The 15 turns of wire produce a choke of 29.5 microhenries. If all is well and 20 amp contact breaker or fuse is not tripped, the electrical power passes through to the gas pressure switch, which is mounted on the electrolyzer. If the gas production rate is greater than the engine requirement, and as a result the gas pressure inside the electrolyzer gets above 5 pounds per square inch, then the gas pressure switch disconnects the electrical supply, because in spite of what I said earlier, the gas pressure switch is set at 5 pounds per square inch, because at 15 pounds a square inch the gas will spontaneously explode. If the gas pressure inside then gets above 5 pounds a square inch, the power to the electrolyzer is cut off and is left off until the pressure inside drops below 5 pounds per square inch, at which point the pressure switch automatically reconnects itself. If all goes well, the gas pressure switch will be closed, and then the electricity from the power supply will be passed onwards. The power is then passed through to both the inverter, the electronics board, and the 110 volts from the inverter is then converted to pulsing DC with about 155 volts of voltage across it. This voltage of the electronics, let me try again. The inverter output is 110 volts AC, so it's passed through a diode bridge which converts it to pulsing DC with a peak value of about 155 volts. This voltage generates HHO gas. The wire connecting the vehicle negative to the electronics board should be very heavy duty, as it's carrying a large current. There is a lot of power stored in a charged battery, so it's important therefore to protect against short circuits in any new wiring being added to a vehicle. If this electrolyzer is to be used with a vehicle, the best overall protection is to have a circuit breaker or fuse connected in the new wiring immediately after the battery. If any unexpected load occurs anywhere in the new circuitry, then the circuit will be disconnected immediately. It is important that the electrolyzer is only connected and operating when the engine is running. While the gas pressure switch should accomplish this, it's no harm to have additional protection in the form of a standard automotive relay in the power supply line as shown in the diagram above. This relay coil can be connected across the electric fuel pump or alternatively wired so it's powered by the ignition switch being turned on. We now come to positioning the electronics. The descriptions and diagrams have been presented with the objective of helping you understand in broad outline what Bob Boyce's electrolyzer is, and very roughly speaking, how it operates. There are practical details which you should discuss in the Working Water Car Forum, as there are experienced people there who will help builders get the details right. It should be realized that the strong, rapidly pulsing currents generated by the electronics cause very powerful magnetic fields. These magnetic fields can disrupt the operation of the circuitry. These fields flow around inside the toroid core, and this creates an area of very reduced magnetic activity in the space in the center of the toroid. For that reason, it would be ideal if the circuit board were placed in that area with the toroid surrounding it. However, the electronics board size does not allow this at the present time, so instead Bob places the toroid inside a custom circular metal housing, something like a biscuit tin made of aluminium, which operates as a Faraday cage to protect against the magnetic fields produced. We come now to supplying the water. The potassium hydroxide is not used up when the electrolyzer is operated. A small amount leaves the electrolyzer in the form of vapor, but this is washed out of the gas in the first bubbler. Two bubblers are used. The first is located beside the electrolyzer and connected to it via a one-way valve. The second bubbler is located close to the engine. From time to time, the water in the bubblers is poured back into the electrolyzer, and that prevents the loss of any potassium hydroxide. Not only does this conserve the potassium hydroxide, but it also protects the engine, as potassium hydroxide has a very bad effect inside the engine itself. The overall water system is like this in broad outline, omitting the electrical safety devices. You've got a water tank which feeds a water pump, which pumps water through a one-way valve into the electrolyzer. The electrolyzer has a water level system, or a water level sensor in the system, and that controls the operation of the water pump, which is also powered from the battery of the vehicle. A probe inside the electrolyzer senses when the average level of the electrolyte has dropped, and it powers up the water pump to inject more water into the electrolyzer. The rate of gas production is so high with the pulse system that the electrolyte level is placed about half the plate height. That is some 3 inches below the tops of the plates. Because of the violent action, the water level sensor needs to be operated from the electrolyzer outside the plates, where the surface of the electrolyzer does not move so violently. A serious issue with an electrolyzer of this type is dealing with the water loss. As the plates have to be spaced closely together, and since the electrolyte between the cells is effectively isolated from the electrolyte in the other cells, driving a mile down the road is liable to lower the water level by half an inch, say 1 centimeter. It is essential to keep replacing the water which is used. Two things have to be dealt with.
One is sensing when the electrolyte level has fallen, and two, creating some device for getting water into each cell. Simple electronics provides the answer to sensing the level of the electrolyte, and a windscreen washer water pump can be used to inject the additional water. A sensor for the water in the cells can be on just one cell. If the water level for any one cell falls below the level in the other cells, then the gas produced in that cell will be slightly less than the other cells, so we'll lose less water until the cell levels match again. Also, Bob recommends that cutting the slots which hold the plates 0.03 of an inch or so larger than the actual thickness of the metal plates. That's not true. It's less than the actual thickness of the metal plates. This effectively blocks electrical leakage between the adjacent cells, but does allow a very gradual migration of water between the cells to help maintain an even water surface across the cell. The water level sensor can be just one stiff stainless steel wire run down each side of any cell. These wires should be insulated to make sure that they do not short circuit to either or both of the plates on each side of them. They should be set so far that their tips are reach the intended surface of the level of the electrolyte, and only the tips of the wire. If the electrolyte level drops below the tip of the wire, sensors then register the resistance between the wires has fallen, indicating that more water is needed. This can then switch the water pump on, which will raise the water level until the electrolyte level reaches the tip of the wire again. Possible circuit for doing this is shown here. When the level of the electrolyte falls below the sensor resistance becomes much higher than it was. The voltage at point A in the circuit then rises to a higher level, which builds up gradually on a capacitor to make sure that it's not just a brief pulse, and when the voltage on the capacitor reaches a realistic level, that switches on the two interconnected transistors, which are wired in what's called a Smith switch, and the Smith trigger switch operates very suddenly and creates a voltage which switches on the final transistor, which then powers a relay, and the relay powers the water pump. The water pump has its own security fuse, but that is, generally speaking, an effective circuit which works well with the requirement here for sensing the particular level of the electrode. You can build a circuit any way you like, or you can use an equivalent circuit of any type you like. The way you do it is entirely up to yourself. The physical layout is shown there if you wish it. The arrangement can be outside the overall system if the arrangement between the last cell and this area of electrolyte is left so that it leaks. The rest of them, of course, don't leak. That levels out the arrangement for that. The alternative, though, is to run a single wire down inside the last cell. As the wire is only physically short in the distance out of the paper as shown, it doesn't actually block the gas flow at all, but it can be used to sense the overall position of the inside water level or electrolyte level. The best way, though, is to allow the final amount of electrolyte to be connected to the last cell. You can do that with a hole through the plate if you wish, or by arranging the slot slightly. The arrangement is quite straightforward, but the arrangement of the welding of the connection stainless steel strap to the end plate is arranged so that the weld is always under water, so that there's no chance whatsoever of there being a spark should anything happen. That includes the connection outside the cell, going through the cell wall to the electrical connection outside of the cell. The arrangement is straightforward and very effective. To combat splashing of the electrolyte, a layer of aquarium matting can be placed over the tops of the plates. In the diagram above, only a few of the 101 plates are shown, in order to keep the drawing narrow enough to fit on the page. The plates on each end have a stainless steel strap welded to them in order to allow for simple and robust electrical connections to be made through the case. The water supply is arranged to feed equal amounts of water to each cell. The design for this supply pipe has recently been improved by Ed Holgate and Tom Thayer. The new design has a water supply pipe with very accurately cut slots in it. The lengths of the slots are directly related to how far along the pipe they are positioned. The objective is to have the same amount of water coming out of each slot, even though the water pressure drops the further along the pipe the slot is located. That water pipe has been housed in an outer pipe which has a hole drilled in it exactly above each of the bodies of electrolyte trapped between the plates. That is, the holes are at 3/16 of an inch spacing. This water supply pipe arrangement works well in practice, and it looks surprisingly like the gas takeoff pipe, which has a series drilled along the top of it. The arrangement works well as it allows a large amount of volume of gas to flow out of the cell, and it makes it difficult for splashes of electrolyte to make it into the pipe. We then have the details of connection to the engine. The Bob Boyce HHO gas engine system produces a very high gas output, that a 25 millimeter 1 inch pipe is needed to carry the gas from the electrolyzer to the engine. Because of the speed of the pressure wave caused if HHO gas were to ignite, no pop-off or shatter disk system has sufficient time to operate. In addition, Bob's system produces the top grade of HHO gas, and as that has the highest energy level possible, it ignites spontaneously at a pressure of just 15 pounds a square inch. To deal with this situation and the very high rate of gas flow which has to be handled, 2 very robust bubblers and 1 robust particle filter need to be used on the output of the electrolyzer, as shown in this diagram here. The gas from the electrolyzer goes through bubbler 1, then bubbler 2, then through the particle filter and on to the air intake of the engine. For people living in America, Bob recommends the use of this particular container. This is a bubbler constructed from whole household pre-filtration unit supplied by the Home Depot, which unfortunately may cost more than $100 each. What you use is of course up to yourself. These units come with a domed cap which needs to be drilled out with a large number of 1/16 of an inch holes, as shown in this diagram. Lots of holes are drilled in the pipe. An important point with this unit is that the flow through the bubbler is in the opposite direction to the arrows molded on the outside of the unit. So ignore the arrows shown on the outside of the unit. Be very careful you don't use the direction shown in the arrows. You use the direction shown in the diagrams in this document. Also, the pressure at which it operates needs to be dropped from normal household water pressure to the 0.5 pounds per square inch gas pressure needed for use as a bubbler. This is achieved by placing the ball valve inside the unit, replacing it with a much weaker version available from the KBI company. Its reference code is KC1000 and costing about $10 US. If you get one, be sure to specify a 0.5 pounds per square inch pressure version, as they have more than one type. It's important that the end cap be a dome variety as shown above. This is necessary as it prevents bubbles joining together before streaming upwards through the water. The particle filter housing is a French-made unit sold by Home Depot under the name of Smart Water and reference number GXWH04F, and it costs under $20 US. As the filter supplied with the unit is not fine enough, a 1 micron filter needs to be bought from Ace Hardware to replace the standard 4 micron filter supplied with the filter housing. This 1 micron filter adapted also acts as a backflash preventer. We come down to practical issues again. No matter which variety of electrolyzer is used, it's essential to put a bubbler between it and the engine intake. This is to prevent any accidental ignition of the gas reaching the electrolysis cell. Again, no electrolyzer should be operated or tested indoors. This is because the gas is lighter than air, so any leak of gas will cause the gas to collect on the ceiling, where it can ignite if triggered by the slightest spark, such as is generated when a light switch is turned on or off. Hydrogen gas escapes very easily indeed, as its atoms are very, very small and get through any tiny crack and even directly through many apparently solid materials. Testing electrolyzers should be done outdoors, at the very least in a very well ventilated locations. Using at least one bubbler is vitally essential as a safety measure. A typical bubbler looks like this. You've got at least 5-inch depth of water from which small bubbles have to pass through to reach the surface. You need some form of protection against splashes before the entrance of the gas output tube. The material, anti-splash material, can be a porous sponge, or it can be a plate protecting against splashes as shown there. Bubbler construction is very simple. It can be any size or shape, provided that the outlet of the entry tube has at least 5 inches of water above it. Plastic is a common choice for material, and fittings are easy to find. It's very important that good seal joints are made when all pipes and wires enter any container which has HHO gas in it. This of course includes the bubbler. Bob Boyce's 112 units produce up to 100 litres per minute of gas, so these need large diameter gas pipes to carry the substantial volume, and the bubblers need to be big as well. It's also a good idea to drill additional holes in the entry pipe from halfway down below the surface of the water in order to create a large number of smaller bubbles. The anti-slosh filling on a baffle plate the anti-slosh filling or a baffle plate in the cap is to prevent the water in the bubbler from splashing up into the exit pipe and be drawn into the engine. Various materials have been used for the filling, including stainless steel wool and plastic pot scourers. The material needs to prevent, or at least minimize, any water passing through it, while at the same time allowing the gas to flow freely through it. Let me stress again that this document does not recommend that you actually build any of the items of equipment discussed here. The HHO gas produced by electrolysis of water is extremely dangerous, ignites instantly, and cannot be stored safely. So this document is strictly for information purposes only. However, to understand the purposes more fully, the following details would need to be considered carefully if somebody decided to actually build one of these high voltage series cell devices. There is a considerable difference between a mixture of hydrogen and oxygen gases, called HHO, and petroleum or gasoline vapor. While they both can serve as fuel for an internal combustion engine, they have considerable differences. One major difference is that HHO gas burns very much faster than petrol vapor. That would not be a problem if the engine was originally designed to burn HHO gas. However, most existing engines are arranged to operate on fossil fuels. If HHO gas is used to improve the burn quality and improve the miles per gallon of a vehicle, no timing of the spark is necessarily needed. However, all recent cars in the USA and elsewhere are fitted with an electronic mixture controller, and if nothing is done about that, then a decrease in miles per gallon may actually occur, as the controller may start pumping more fuel into the engine when it sees a change in the quality of the exhaust. Good information on how to deal with this can be found at the website free-energy-info.com /d17.pdf, which includes detail of how to deal with the controller, or in the previous document of this appendix. If an engine is run without any fossil fuel at all, then no timing adjuster needs to be made at all. Let me rephrase that. If an engine is run without any fossil fuel at all, then timing adjustments do need to be made. Hydrocarbon fuels have large molecules which do not burn fast enough to be efficient fuels. Inside the cylinder of an engine, what happens is that for the first fraction of a second after the spark, the plug, fires, the molecules inside the cylinder split up into smaller particles, and those smaller particles burn so fast that it can be described as an explosion. That is, in this diagram you can see what I'm talking about. The compression stroke compresses a petrol vapor in the top of the cylinder before the spark occurs. The spark occurs before the cylinder reaches the exact top, called top dead center. When it reaches top dead center, the molecules are in the process of splitting into smaller particles, and after the piston has started its downward movement, having passed the top of its stroke, the high-speed burn described as an explosion takes place. That's usually about 10 degrees after top dead center in most engines which run on petrol. However, if you're going to operate on HHO as a fuel, HHO operates 1,000 times faster than petrol droplets. The spark, therefore, needs to happen after the top dead center point. There would be a real problem if you just substitute HHO gas mix for the petrol vapor, because the HHO gas has very small molecule sizes to begin with, and those molecules don't need any kind of breaking up, and they burn instantly, and what's more, they're in the ideal ratio of hydrogen to oxygen to do an immediate conversion into water. You have a real problem though with this operation, because the If the spark happens as in a petrol engine without any adjustment, the piston will not have reached the top when you get an explosion, and that is a major problem as far as the crankcase and connecting shaft are concerned. The power stroke is in the wrong direction. You do not want that on an engine. The explosion of HHO gas is almost instantaneous, and it attempts to force the piston downwards. Unfortunately, the crankshaft is trying to drive the piston upwards past the top dead center point, so the explosion will not help the engine run. Instead, the explosion will cause the crankshaft to stop rotation, and it will produce excessive pressure on the wall of the cylinder. We do not want that to happen. The solution is to delay the spark until the piston has reached the position in the rotation where we want the explosion to take place. That is, in exactly the same place as it did when using petrol as a fuel. In the example above, the spark would be retarded or delayed from the 8 degrees before top dead center to the 10 degrees after TDC, or top dead center. That is 18 degrees overall. The spark is retarded because it needs to occur later in the rotation of the crankshaft. The amount of retardation may vary from engine to engine, but with HHO gas, the spark must never occur before top dead center, and it's preferable that the crankshaft has rotated some degrees past top dead center, so that most of the push from the piston goes to turn the crankshaft, and as little as possible in compressing the crankshaft. It should be mentioned that, strictly speaking, if you ignite pure HHO gas, it converts back into water, which has a volume of nearly 2,000 times less than the gas. That means that actually you would get an implosion if you ignite pure HHO gas. That doesn't make any difference to air damage through the shock wave sound produced by the implosion. So what you generally do if you're feeding only HHO gas to an engine to make it run and drive, say, an alternator or a compression engine of some description, then you add cold water droplets to the incoming air, and it is the droplets turning to flash steam that creates positive pressure inside the cylinders of the engine. Please bear that in mind, and this is only a generalized description of what you should understand when you want to use HHO fuel. We then come to diesel engines. Diesel engines do not have spark plugs, and so there's no timing alterations needed with them. The problem is any volume of HHO gas up to 80% of the cylinder contents can be added into the air entering a diesel engine, and it automatically helps the miles per gallon performance of the diesel engine. If a really large volume of HHO gas is available, then the diesel engine is set to tick over on diesel, and HHO gas is then added to rev the engine up and provide the power. The amount of HHO gas should not exceed 4 times the amount of diesel, as engine overheating will occur if it does. Roy McAllister has been running internal combustion engines on hydrogen and many mixtures of hydrogen and other fuels for 40 years now. He advises that anybody interested in implementing a system like this to start with a cylinder engine of 5 horsepower or less. That way the techniques are easily learned and experience is gained in tuning a simple engine running on the new fuel. So let us assume that we're going to convert a small generator engine. How do we do that? First, we obtain our supply of the new fuel. In this case, let us assume that we produce HHO gas using a multi-cell high-voltage series electrolyser as described earlier. This unit has an electrical cutoff operated by a pressure switch which operates at, say, 5 pounds a square inch. Assuming that the electrolyzer is capable of producing a sufficient volume of gas, this is roughly equivalent to a hydrogen bottle with its pressure regulators. In broad outline, the gas supply should look like this. You've a water tank and a pump feeding your electrolyzer, which might have 60 cells in it. Then you have the electrics, which drives the electrolyzer itself. Then the gas is produced going through two bubblers. Then you put a needle valve in the feed to the engine. The physical connection to the engine is via a 6mm or 1/4 inch stainless steel pipe fitted with a standard knob operated needle valve. The carburetor is removed altogether to allow maximum airflow into the engine, or failing this, the throttle valve of the carburetor is opened wide and secured in that position. The stainless steel gas pipe has its diameter reduced further by the use of a nozzle with an internal diameter of 1mm or so. That's 1/16 of an inch, about the size of a hypodermic needle used by a vet. An HHO gas has very small molecules and will flow very freely through tiny openings. The nozzle tip is pushed close to the intake valve, and the gas feed pipe is secured in place to ensure no movement. When the engine is about to be started, the needle valve can be hand adjusted to give a suitable level of gas flow to maintain the tick over. But before that can happen, the timing of the spark needs to be adjusted. There are two main ways to adjust the timing. The first is mechanical, where an adjustment is made to the mechanism which triggers the spark. Some small engines may well not have a convenient way to adjust the timing by as much as is needed for this application. The second way is to delay the spark by an adjustable electronic circuit, for instance an NE555 monostable driving a field effect transistor. This can either be built or bought ready-made. One supplier, which offers a dashboard mounted, manually operated, controlled, readily built ignition delay unit, is msdignition.com /1 timing controls, and there are others who also supply ready-made units. We then come to the issue of waste spark. As already discussed in earlier text, there is one other very important consideration with small engines, and that is the way in which the spark is generated. With a 4-stroke engine, the crankshaft rotates twice for every power stroke. The spark plug is only needed to fire every second time the piston approaches its highest position in the cylinder. This is not particularly convenient for small engine manufacturers, so some simplify matters by generating a spark on every revolution. The extra spark is not needed. It contributes nothing to the operation of the engine, and so is called a waste spark. The waste spark does not matter for an engine running on fossil fuel vapor, but it does matter very much if the fuel is switched to HHO gas. As has been shown in the earlier diagrams, it is necessary to retard or delay the spark by some 18 degrees. So when using HHO gas, due to its very much faster ignition rate, delaying the HHO fuel ignition point until after top dead center sorts out the situation in an entirely satisfactory manner for the power stroke of the engine. However, if the engine generates a spurious waste spark, then that waste spark does cause a serious problem. In the case of the fossil fuel, any waste spark will occur towards the end of the exhaust stroke. So the waste spark in a petrol engine occurs while the petrol exhaust valve is open and the burnt gases are being expelled. So having a spark in burnt gases makes no difference to a petrol engine. And so a petrol powered standby generator can run quite happily on petrol but not on HHO. HHO gas ignites so fast that you have a real problem, because if you convert to HHO with the bubbler operating and the needle valve open a bit, the trouble is if the spark occurs 18 degrees before top dead center, 8 degrees before top dead center, then the entry valve, the inlet valve for the hydroxy fuel is open, and the gas above the top of the cylinder is HHO gas, and the spark will occur when the valve is open and when there's HHO gas in the cylinder and all the way through the intake and needle valve to the gas in the second bubbler. That will cause an explosion in your engine, and it will happen every single time. There is absolutely no question about it happening. It will happen, and it will cause an explosion of the gas in the second bubbler. It will blow the gas cap off, but not fast enough to stop the flame front. But the flame front, if you're lucky, will be blocked by the water in the bubbler, and failing that, will be blocked by the water in the second bubbler, which is, I suppose technically you could call it the first bubbler, but it will be the next bubbler down the line as the far flame front passes down the pipe towards the electrolyzer. But this is a major problem for the operating of a standby generator using just HHO gas. You can operate a standby generator with HHO gas very satisfactorily. In fact, it's something that's relatively easy to do, and it works extremely well and provides a lot of excess free energy, which can be used to run quite a lot of electrical equipment. But once some experience has been gained in operating a single cylinder engine on HHO gas, the move to a full-sized engine is not very difficult. Each cylinder of the large engine is pretty much the same as the small engine, except for running a small tube down the carburetor intake of each cylinder. It is a more convenient economic method to use the existing intake manifold, leave the throttle wide open, and run the HHO gas pipe into the manifold. A flexible steel pipe section should be used to absorb the vibration of the engine relative to the electrolyzer. Roy McAllister suggests using a knob-operated needle valve to set the idling speed to about 1000 RPM and replacing a throttle-operated lever valve in parallel with it for applying more power to the engine. It's not immediately clear to me why this method is recommended, as the knob-operated needle valve to set the idling rate appears to be redundant. There appears to be no particular reason why a screw adjustment could not be used on the lever valve linked to the accelerator pedal of the vehicle. If that were done, then the throttle screw would be used to set the idle rate and the screw locked in position. That way the needle valve and two Y connectors could be dispensed with. The only possible reason which suggests itself is that there is slightly less physical construction needed for the recommended way, which is shown here. That is, the gas from the bubblers goes through a Y connector to through a needle valve on this side and an ordinary throttle valve on the other side, and the outputs then combined again with another Y connector to feed on to the manifold of the engine itself, and so enters the engine with the normal intake air of the vehicle. There is a supplier of flexible tubing suitable for this sort of work, and that is tightflexcommercial.com, but there will be many other suppliers. we have to consider the implications of engine size limits. A 101 plate Bob Boyce electrolyser, accurately built, properly cleansed and conditioned, produces 50 litres a minute of HHO gas continuously when tuned properly, and can sustain short bursts of 100 litres per minute. It is really not possible to say how much HHO gas is needed to operate any particular engine, as the energy requirement varies so much from engine to engine, even though they may have the same engine capacity. However, it's a very rough ballpark figure. You could consider it being for a 2-litre engine to run satisfactorily on 100 litres per minute of HHO gas. Please remember that when flow rates like 100 litres per minute or more are being dealt with, that it is essential to use large diameter pipe, say 1-inch diameter, from the electrolyser onwards. Also, the bubblers need to be physically larger. It is essential to avoid any possibility of large HHO gas bubbles forming a continuous path through the water in the bubbler, so that it would allow a flame front to pass directly through the water in the bubbler, which is exactly what the bubbler is there to prevent. So don't skimp on the size of bubblers, especially as they will only be half filled when the gas flow rate is very high. Bob Boyce explains the present limit on gas production as follows. The impedance of the micrometals T650 toroidal core reaches a maximum at 36 square inches per plate. It is possible to use one long 201 plate electrolyser powered with double the voltage. The problem is that we can't increase the current density, as it would increase the toroid temperature, which would cause the permeability to decrease. However, we can increase the voltage without worrying about increasing the toroid. So going to 240 volts AC is not a problem which will raise the temperature of the toroid. A 201 plate electrolyser could achieve 200 litres per minute, which would be able to operate or power a 3 to 4 litre engine. Ideally, an electrolyser of that type would have a micropressor controller circuit board, as that would generate faster pulse transition speeds than the present circuit board. An electrolyser of that type would need a revised case design to take stainless steel plates which are 9 inches wide and 6 inches tall. The electrolyte level would then be set to a 4-inch depth, giving the same 36 square inches of active plate area. A 101 plate electrolyser measures about 20 inches in length. A 201 plate unit would be about 40 inches long, and so would fit into the boot or trunk of a car or the back of a pickup. This means that there is still more potential left in the T650 toroid before there is any need to find a larger toroid. An 8-inch toroid, a 101 plate unit, could fuel an engine up to 4 litres capacity. A 10-inch toroid driving a 101 plate unit could fuel a 5-litre engine. In these cases, the plate area would be larger than 6 by 6 inches, because with a larger toroid, the current can be increased without overheating the toroid and lowering its permeability. The information for micrometals is that their hydraulic press can make toroids up to 8 inches in diameter, but the success rate diminishes as the diameter increases. As it is, the success rate for making a 6.5-inch diameter is their best economical rate. For larger diameters, the cost of the increased failure rate is passed on to the buyers. There is word of a small private Canadian firm that is working with 5-gallon pails of mining tailings to extract high permeability materials which can be used to make larger toroids. They crush the tailings into fine powder with a huge milling stone, then pass the powder under a magnet to collect the magnetic materials. They do this several times, and they mix the remaining material with a binder to form a toroid. Every company in the toroid making industry has their own proprietary formula for making toroids. This Canadian company's 6.5-inch toroid matches the Micrometal's 600 6T50 pretty well. If there is enough interest, they can quote a quantity rate for a larger toroid. It might be remarked in passing that there's nothing to stop you using two systems with 6.5-inch toroids to power a larger engine. But that, of course, is a matter that is up to builders. Stationary applications are usually something of great interest, and some people wish to try home applications with an electrolyser of this type. They ask about powering the unit directly from the mains rather than from the electrical system of a vehicle. This is a practical proposition, and it has the advantage that size and weight are no longer of any great importance. The circuit would alter very slightly for this application as shown here. You have a very heavy duty 12-volt power supply or 110 volt mains inverter powering the diode bridge and feeding the circuit that we've been looking at before. The circuit has two capacitors to smooth the DC output to the unit. But with a mains unit, with using a mains rather than with an inverter, to create 110 volts AC, a car battery charger or mains power supply unit is needed to provide the same voltage that the vehicle electrics would have provided. It would probably be worth putting a large value capacitor across the output of the car battery charger to help smooth out the voltage ripple. So you produce the circuit for doing that like this. Instead of using a vehicle battery, an inverter, you use a heavy-duty 12-volt mains power supply. That's not a particularly cheap unit. It's a large and heavy device to be able to supply continuous power at a high level. The power itself can be either produced with an inverter or via the mains. This is the 220 volt mains, though it could be 110 volt, powering a power supply. The power supply itself, it acts then as the system input for the circuit as before, using exactly the same components as before. You can operate either 220 volt system with 200 plates or 101 plate 100 section normal American operation using 110 volt mains. It really doesn't matter what the mains voltage is, because the power supply is adjusted for the actual supply from the mains that it is expected to operate with. So you can power any form of stationary version of the electrolyser with a mains operated unit. Bob has had experiences which are interesting. Bob had an electronics business down in South Florida where he owned and sponsored a small boat racing team through his business, starting in 1988. He had a machine shop behind his business where he did engine work. He worked on engines for other racers and a local mini-sub researcher outfit which was building surface running drone type boats for the DEA. he delved into hydrogen research and started building small electrolyzers using distilled water mixed with an electrolyte. He then resonated the plates to improve the efficiency of the units. He discovered with the right frequencies he was able to generate monatomic hydrogen and oxygen rather than the more common diatomic versions of these gases. When the monatomic gases are burnt, they produce about 4 times the energy output produced by burning the more common diatomic version. About 4% of diatomic hydrogen in air is needed to produce the same power as petrol, while slightly less than 1% of monatomic hydrogen in air is needed for the same power. The only drawback is that when stored at pressure, monatomic hydrogen reverts to its more common diatomic form. To avoid this, the gas must be produced on demand and used right away. Bob used modified liquid petroleum carburetors on the boat engines to let them run directly on the gas produced by his electrolyzers. Bob also converted an old Chrysler car with a slant 6-cylinder engine to run on the hydrogen setup and tested it in his workshop. He replaced the factory ignition with a higher energy dual coil system and added an optical pickup to the crankshaft at the oil pump drive tank to allow external ignition timing adjustments. He used Bosch Platinum series spark plugs. Bob never published anything about what he was working on, and he always stated that his boats were running on hydrogen fuel, which was allowed by the race operators. Many years later, he found that he had stumbled on what was already discovered and known as Brown's gas, and there were companies selling the equipment and plans to make it. Bob's electrolyzer is fairly simple to make, but requires a lot of plates made of 316 stainless steel, able to withstand the more exotic electrolytes, which are more efficient, and a plastic box to contain the plates. 8-inch spacers to keep the rows of plates apart, the electrolyte, and an adjustable frequency modified pseudo-sine wave inverter to drive the electronics. A total of 101 plates, 6 inches square, are used to give a large surface area. These have their surface scarred with coarse sandpaper in an X pattern to give a fine crosshatch grain, which added sharp points to the surface of the plates. This is found to improve the efficiency of the electrolysis. The box has 2 threaded ports. One is threaded for injection replacement distilled water, and a larger one for extracting the HHO gas. Under the top cover is a piece of plastic matting to prevent sloshing. It is very important to keep the electrolyte level below the tops of the plates to prevent current bypassing any cells and creating excessive water vapor. Bob places a 5 pounds per square inch pressure cut-off switch in a T on the water injection port that shuts the drive off down when the pressure in the unit reaches 5 pounds per square inch. This allows the unit to be able to supply on demand without building up too much pressure in low demand situations. He builds a bubbler from a large home cartridge type water filter to prevent any backfire from travelling back up along the gas feed pipe to the electrolyzer. Without some form of bubbler, there is the risk of electrolyzer igniting if a flame front from the engine flows back to it. The copper mesh screens designed for welding gases will not work, as hydrogen gas has a much higher flame propagation speed which passes straight through the copper mesh. The bubbler should be placed close to the engine so as to limit the amount of recombination of the gases from the monatomic to diatomic versions. The HHO gas should be fed to the vapor portion of a liquid petroleum gas carburetor system. The carburetor will have to be modified for hydrogen use, that is a different mixture rate than propane, and adjusted for best performance of the system. Bob found that the best electrolyzers to use were sodium hydroxide, that's NaOH, and potassium hydroxide, that's KOH. While sodium hydroxide works well and is much easier to get, called Red Devil lye found in most department stores in America, than the slightly more efficient potassium hydroxide, whatever is used, you need to be very careful what construction materials are used. Make absolutely sure that the construction materials are compatible with the chosen electrolyte. Plexiglass acrylic sheet was what Bob used for the box. Never use glass containers for mixing or storing potassium hydroxide. Bob has never had the chance to drive the test Chrysler on the road with the system. Instead, he placed the rear end on jack-up stands and ran the engine under no load conditions in drive just to test and tune the system and to get an idea of how well the engine held up on the hydrogen fuel. The vehicle was run for a mileometer recorded distance of 1,000 miles in this setup, with the hydrogen being fully powered by the alternator of the vehicle. With the vehicle running at idle, the drive electronics consumed approximately 4 to 4.3 amps at 13.8 volts DC, with the rear wheels off the ground and the engine running with the vehicle speedometer registering 60 miles per hour. The drive electronics drew approximately 10.9 to 11.6 amps at 13.8 volts DC. The unit does not use normal brute force electrolysis when operating in high efficiency mode. It relies mainly on a chemical reaction that takes place between the electrolyte used and the metal plates, which is maintained by an electrical energy applied and stimulated into higher frequency by the application of multiple harmonic resonances which help to tickle the molecules apart. Multiple cells in series are used to lower the voltage per cell and limit the control current flow in order to reduce the production of water vapor. It relies on the large surface area of the total number of cells to get the required volume of fuel vapor output. In the first prototype of his design, Bob used a custom-built controller driver which allowed a lot of adjustments so that performances could be tested using different frequencies, voltages and waveforms individually. The result was that a pattern of 3 interwoven square waves rich in harmonics that then produced the optimum frequency efficiency. When Bob had the basics figured out, he realized that he could just replace the custom controller driver unit with a modified inverter, which is much easier than building a unit from scratch. He experimented using a 300 watt pseudo sine wave inverter that had been modified so the base frequency could be adjusted between 700 and 800 cycles per second. The step sine wave output was fed through a bridge rectifier which turns each stepped sine wave into 2 positive stepped half waves. Each of these half waves had 8 steps, so a single cycle was turned into 16 steps. The resulting output, while not consisting of intermixed square waves, was still rich in harmonics, and it was much easier to adjust the point of resonance when trying to tune 3 separate frequencies. Please note that these inverters are no longer available for purchase, and that Bob's triple oscillator board design is far superior anyway, giving more than double the output produced by the old inverter, and is definitely the board to use with Bob's electrolyzer. The frequency range can change depending on the number of steps in the pseudo sine wave of the inverter you choose, since not all inverters are created equal. The desired effect is caused by the multiple harmonic resonances in the inverter output at higher frequencies. you will know that when you hit resonance, that the dynamic increase in gas output shows the difference. The frequency does vary a bit depending on what electrolyte is used, the concentrate of the electrolyte solution, the temperature of the electrolyte, the water purity, etc., etc. Bear in mind that Bob's electrolyzer tank was large enough to hold 61 plates of 316 grade stainless steel, which are 6 inches by 6 inches square, spaced 1/8 of an inch apart, to create 60 cells in series, with 130 volt DC power from the inverter to the bridge rectifier applied to the end plates only. That gave 4,320 square inches of surface area, plenty of surface area to produce enough fuel for a vehicle engine. The best electrolyte for efficiency was potassium hydroxide, and the electrolyte level must be kept below the tops of the plates to prevent any current from bypassing the plates and creating excess water vapor through heating. Distilled water was used to prevent contamination of the electrolyte, which would result in reduced performance and efficiency. The unit had 316 grade stainless steel wires welded to the tops of the end plates. The other ends of the wires were welded to 316 grade stainless steel bolts, which passed through the holes in the end of the container with rubber O-ring gaskets inside and outside, located above the liquid level. There was a PVC spray bar attached to the inside of the chamber to the water injection port, with tiny holes along its length on the underside to supply replacement water evenly to the cells when the water pump was switched on. A backflow prevention valve on top of the T was used to keep the vase from flowing into the water lines. There was a mat of interwoven plastic fibers, air conditioner filter material, cut and fitted to the top of the plates to help prevent sloshing. Do not use fiberglass mat, which could cause severe reaction with some electrolytes like potassium hydroxide. It's very important to understand that unless the engine is originally designed for or later modified for running on vapor fuels such as liquid petroleum gas, natural gas, that water mist injection be added, unless the engine has the proper valves for vapor fuel. The stock valves will not survive for extended run times on vapor fuel of any kind without additional cooling of some sort. This is an issue of valve design by the vehicle manufacturers, not something detrimental because of HHO gas combustion. The manufacturers want to prevent their cars from being adapted to high mileage operation without adverse effects, so they design the valves to fail if not cooled by excess raw fossil fuel. This document can be downloaded from free-energy-info.com.